Let's look at the last question from our belts tutorial. So question 3, it says that an electric motor drives an exhaust fan. The following information is given in the table as given over here. So we've got information regarding the motor pulley. So diameter is 400, rep angle is 2.5 radians, coefficient of friction is 0.3, speed at which the motor pulley is rotating is 700 revolutions per minute, and the power transmitted is 22.5. For the fan pulley, diameter is given as 1600 mm, coefficient of friction is 0.25, and the rep angle is 3.78. And then what we are to do is we are to calculate the width of the belt that is required if the thickness of the belt is 5 mm. The maximum stress in the belt is given as 2.3 megapascal, and the density of the belt is given as 1000 kg cubed. And then we have to take into account the effect of centrifugal tension. So what happens is most of the information that we'll use will be from the motor pulley, because the motion is provided by the motor. So we'll look at the speed of the pulley on the motor. We'll look at the diameter of the pulley which is mounted onto the motor. So we'll look at our solution now. So what happens is the power transmitted is 22.5, the thickness of the belt is given as 5 mm, the density is 1000 kg per meter cube. The diameter that I have listed here is the diameter of the pulley that is mounted onto the motor. So this is the diameter of the motor pulley, because the motor is actually providing the motion to the belt. So the pulley that is mounted onto the motor has a diameter of 400 mm. The speed of the pulley is given as 700 revolutions per minute. So the velocity is simply given as pi dn upon 60. So pi, the diameter that I'm using is the diameter of the pulley that is mounted onto the motor, which was 400 mm. So 0.4 times 700 divided by 60. So the velocity of the belt is 14.66 meter per second. The stress, the maximum stress in the belt is 2.3 megapascal. Now what I'm doing here is I'm looking at the product of the value of rep angle times the coefficient of friction for the respective pulleys. So theta m is the rep angle for the motor pulley, and then mu m is the coefficient of friction of the pulley mounted onto the motor. So these were 2.5 and 0.3 respectively. So 2.5 and 0.3 respectively. So 2.5 times 0.3 is 0.75. And then what I'm doing is this is looking at the fan pulley. So rep angle for the fan pulley was 3.78. Coefficient of friction of the fan pulley was 0.25. So once I do the product, I get 0.945. And then in our lectures, I think it was given in our notes that we'll use the product which gives you the least value. So when you look at this product of theta m times mu m is 0.75, and the product of theta f and mu f is 0.95. So the least is 0.75. So therefore when I calculate my tension ratio, which is T1 over T2 is equals to exponential mu theta. So in place of mu, I will replace the value of 0.3, and for my lap angle I will substitute 2.5. So these values are done with respect to this understanding that the product of whichever one is the smallest, we'll use that. So our tension ratio T1 over T2 simply equates to 2.12. So therefore T1 is nothing but T1 is simply 2.12 T2. What happens is the power that is transmitted by this system is power is equals to T1 minus T2 times your linear velocity, and we know that power is 22.5 kilowatt. The velocity, linear velocity, is over here, which is 14.66. So T1 minus T2 is nothing but your power of 22.5 kilowatt divided by your velocity, which is 14.66. So you will get that T1 minus T2 is 1534.79, and we know that T1 is 2.12 T2. So substituting that over here, so we get 2.12 T2 minus T2 is equals to 1534.79. So therefore T2 is 1370.35, and then using our tension ratio, that T1 is 2.12 times T2, our T1 equates to 2905.14 Newton. So this was done in order to find the tension in the tight side and the slack side. So T1 is as such. Moving on. So the next thing is, we know that our maximum stress is simply equals to your cross-sectional area times the stress. So maximum tension is sigma I. So the maximum tension is simply equals to sigma I, and cross-sectional area is nothing but the width of the belt times the thickness of the belt. So the maximum stress was given as 2.3 megapascal times width of the belt we don't know, so put as B, and the thickness of the belt was given as 5 mm. So converting it to meters, so we get your maximum stress T is nothing but 11,500 B, because B is the width of the belt that we are solving for. The mass of the belt is given as rho times your volume, and volume is nothing but the cross-sectional area times the length of the belt. So density times the cross-sectional area is given as width of the belt times the thickness of the belt times the length of the belt. So what we do over here is, the density was given as 1000, the width of the belt is B, the thickness of the belt is given as 5 mm, so converting that to meters, and then for the length of the belt we use simply 1. So the length of the belt is, the mass of the belt is simply 5B. So the total tension or the maximum tension is 11,500 B. The mass of the belt is 5B. The next thing is, we can calculate our centrifugal tension. The centrifugal tension is given as mv squared. Mass of the belt is 5B. The velocity of the belt was 14.66. So your centrifugal tension equates to 1074.58 B newtons. So we have calculated our centrifugal tension in terms of the width of the belt. Now the next thing is that this definition is given in your lecture notes, so which states that your maximum tension is nothing but equal to the total tension on the tight side, which is simply equals to T1 plus TC. So your maximum tension or the total tension on the tight side is simply 11,500 B. T1 was 2,905.14 Newton, and your TC is given as such. So what we do is, 11,500 B is equals to 2,905.14 plus 1,074.58 B. So making B of this subject of the formula, we simply solve that the width of the belt is nothing but equal to 0.278 meters. You can even round it up to the next tenth of a mm, so you can say that the width of the belt is 280 mm, but you can leave your answer as such. So that basically brings us to the end of the belts tutorial.